Hello. As part of my research with the University of Reading, I've been looking into how type systems are designed. And in this presentation, I want to talk about the consequences of some of those design decisions in the context of the digital infrastructure for global type. And how some of those decisions can influence how we talk about type, how we think about type, and how we work with type. And I'll start from a core concept in our industry, namely the font, intentionally sidestepping the high-level conceptions, the historical framings, the various domain-specific perspectives, or even the general confusions that typography is fraught with. I'm going to go directly to the technical sense of the word. This is the closest thing that we have to a wide consensus, and it's the definition from the Unicode standard, where a glyph is an abstract form that represents a concrete image of a glyph representation having been imaged. And the character is a unit of information used for the organization, control, or representation of textual data. A few points here. The character is a concept that is central to Unicode's encoding model. And we can see how the definition put forward by the organization centers that work. Second, the distinction between character and glyph is an important one, but I'll come back to that later on. For now, though, I'd like to note the contrast between the precise language with which character and glyph are defined and the vagueness of a collection that is assigned to the idea of a font. In the context of standard specifications, vague language is usually seen not as a defect, but rather as an intentional acknowledgement that information may be acted upon by various other different applications. In other words, it's left open-ended on purpose, declaring it as out of scope for the standard. But while that empowers people to open it up for interpretation, it also can obstruct the ways in which those applications mediate the meaning of what a collection is. For the visually inclined, a collection might mean the character data with the glyph data rendered visually in an interface. Or it might mean the glyph data laid out in a table. For someone working directly with the coded characters, it can also be a list of mnemonic representations. These are different levels of abstractions, each with different affordances, terminology, and conceptual spectrums. The idea of a collection is always mediated by the institutional, organizational practices and worldviews of those who develop these representations. Whatever the level of abstraction, though, the one thing different terminologies have in common is that a collection of glyphs is always an abstract, dematerialized construct, as opposed to analog collections like a hot metal matrix or a phototype disk. But this is a relatively recent way of thinking about digital fonts. And I want to briefly go back to the earliest stages of digital type, when the idea of a font involved much more than software. This machine is the small-scale experimental machine designed and built at the University of Manchester in 1947. This is actually a replica built by the Computer Conservation Society in 1998. It was meant to show that a new type of cathode ray tube was feasible. The Williams-Kilburn tube, as it was later referred to, stored computer bits as dots on the screen surface, each dot lasting a fraction of a second before fading. The Williams tube was the first commercial electronic random access memory, and the computer was the first machine that had all of the components now classically regarded as familiar of the basic digital computer: a processor, a memory, and a monitor to display information. The reason this is relevant to digital typography is that among the first digital images generated on that monitor were the first digital characters, or more precisely, the first digitally stored configuration of dots that would appear as character images. This is a close-up of the display from the Williams-Kilburn tube in its first iteration. The bright spots represent ones and the dim spots represent zeros, which is data in a raw binary format. This is the second iteration of December 1947, which stored twice the amount of bits on a standard CRT for a period of hours. The demo was manually programmed, so there was nothing automated behind the character images. There was simply a one-to-one mapping between the computer bits of memory and the visible dots that made up the characters. The first computer-generated character images, however, came along almost a decade later. In the late 50s, a company called Digital Equipment Corporation was spun out of MIT, where its founders initially did research on the whirlwind computer. This also stored bits on the screen, although with slightly different internal mechanics, but not that dissimilar working principles from the Williams-Kilburn tube. DEC was responsible for the PDP line of computers, with the PDP-1 being the first general purpose interactive mini computer built around modularity. The Type 33 display, a variation of the Type 30, had special circuitry that could generate character images. This was technically referred to as a character generator, but for all intents and purposes, this was as close as possible to what could be called a font. This device was sold and distributed as a standalone device with the sole purpose of generating characters. Those characters were designed using a light pen, like the whirlwind computer, encoded into machine code and activated by a set of instructions, not unlike how digital fonts currently work. Between the whirlwind's CRT and the Type 33, the purpose of the screen changed, going from memory to imaging. An important note here is that this is when the one-to-one mapping between a pixel and a bit in computer memory shifts to a one-to-one mapping from a computer word of memory to a character, or from a character code to a character. Admittedly, the characters weren't designed by a type designer or typeset by a typographer, which is presumably why these developments are overlooked in the typography literature, but typographic decisions were made: where to place each dot, how to make the best use of the number of dots available in a way that the characters are recognizable and legible. This design by Pixel is the precursor of much discussed later projects such as Herald Unger's demo. All of these decisions were hardwired in the logical circuitry of the physical device itself, which means that a digital font, in this case, was a physical thing, an arguably different notion of what digital is associated with today. And going from this notion of a font to a dematerialized one is an interesting case study in systems design and the consequences of those design decisions. CRT typesetters in the early 60s and 70s integrated character generators in what can be best described as computer-like equipment, an assembly of mechanical, digital, and optical components usually sold as an integrated system to do high-resolution typography. At that time, though, there were many different display systems being developed. There were systems that used various techniques to control the light gun inside the CRT, and different techniques to form characters on the face of the tube. Some even used predefined stencils and steel meshes. The end result depended on other material variables as well. From the granularity of the phosphor coating to the accuracy of the ray gun in the cathode tube, the size and shape of the glass, to various processing signal and voltage management components. All of that diversity in different display technologies inevitably led to a diversity in font making methods. Type vendors use different matrix, vector, or raster scan generators in their typesetting equipment. And different representations were best suited to different encodings and formats. Each vendor had their own character sets and even their own page description languages, all usually proprietary. Each system was designed like this, by putting custom hardware and software together. And I want to emphasize that engaging with and understanding all of these physical properties, how they constrain and shape the appearance of letter shapes on the screen, is what enables systems to be designed in a way in which characters could be improved. Going from simple configurations of dots, for example, in alphanumeric displays, to characters that would simulate the appearance of traditional typefaces. This is a screenshot of what is widely considered as the first digital font, and the machine that produced it, Hell Digiset, which used a raster scan stroke generator, could set 6-point type. In a way, it can be argued that designing computer-stored and rendered type hinges on this ability to decide what and how all of these subsystems for representing, encoding, and rendering type are patched together. From a theoretical perspective, the diversity of early systems contributed to new terminology and new knowledge. Things like character codes, encodings, vectors, and bitmap representations, rasters. These are all foundational concepts that underpin digital type today and were developed during this period. However, from an industry perspective, particularly from the point of view of large systems manufacturers, this was problematic. The main issue with all of that diversity was essentially one of cost. Virtually with every unique configuration of a computer and display system, each with own sets of requirements, fresh graphics, software needed to be written in order to support it. Software was not portable from one system to another. This need to find cost-effective solutions to scaling problems created a lot of pressure to standardize. In information exchange, it was straightforward to transmit text, but not images. So standardizing computer graphics was a much more challenging problem. Attempts were made, workshops were convened, but little consensus was reached. What did gain traction, however, was to develop software for entire classes of devices. This is when designing large-scale systems started to dispense with the particularities of a certain configuration of hardware and software, and instead prioritize high-level and general-purpose abstractions. This is a significant departure from the previous design approaches and promotes a different type of thinking, where one-size-fits-all solutions are not only necessary, but desirable. This approach defined what would become a dominant trend in the design of type systems, system that aimed at being first device-independent and then script-agnostic, or in other words, universal. To this end, the company that did the most in terms of setting the precedents for how large-scale type systems are designed was Xerox. People working at Xerox lobbied the standards working groups and asked for universal standards. They developed their own standards, which was not common at the time. IBM had the EBCDIC standard, for example, which as a practice has its roots in typewriters, teletexts, where each manufacturer maintained their own character set for each market. They developed their own representations, formats, specifications, and most importantly, their own glossary, where we can see the early versions what would become standardized terminology. They developed their own font design systems with spline and bitmap editors, and the interfaces of which are prototypical of modern font editors. Their own description language that was positioned as a printing standard and as a universal interface, and pushed for a universal notion of the text. The author of this paper went on to co-found Unicode. Combined, all of these developments proved a significant inflection point which radically changed how systems for making type are designed. From a diverse ecosystem of developers and designers doing purpose-built, domain-specific systems to device-agnostic, standardized pieces of software. And growing from the engineering silos of the early 50s and 60s, we can see a trajectory towards centralization. A multitude of methods of representing, encoding, storing, and rendering digital type information converging into so-called universal solutions. This concentrates decision power into the hands of a relatively small collective of experts, and when that collective supported, funded, or lobbied by companies with various economic interests, establishes a new industry standard, for example, by subsuming previous standards, then merges with an international standard to become a global standard, and gets wide support by dominant operating systems, then that their collective shared model tend to become dominant models in type making. The problem is that the models behind these design decisions are operational, meaning that they describe how the terminology operates or should operate. That distinction between character and glyph I mentioned at the start, that is Unicode's character glyph model, and it describes strictly a mapping scheme from low-level machine codes to graphical representations, which separate content from appearance. This idea of separation goes back to Becker's and Newman's work I showed earlier, but it did not originate from Xerox. McCarthy's memorandum at Stanford in 1972, where he proposed an arbitrary character set, which anticipated many of Unicode's design decisions, shows that these ideas were previously discussed in computer science circles. But most importantly, it is very candid with consent to typography, reflecting a general attitude of the time when typographic considerations were not systems design considerations. They were intentionally left out. And I want to emphasize here that the basic blueprint for type systems was architected in the US in the 1970s by computer scientists working with local knowledge, starting from a pared down Latin character set, and with typography initially ignored and later separated from content. This type of thinking is inherited from earlier encoding schemes constrained by physical capacities of early display systems, which employ the one-to-one mapping between the character codes and the imaged output. And we can start to see how terms and concepts from the very limited local early work have survived into today's ostensibly agnostic environment, but impose limitations conceptually and technically. For example, in modern font making, there is almost nearing zero development in complex scripts that relies on one-to-one mapping. But instead, it's usually a one-to-many approach, one character to multiple glyphs. The issues that emerge around this are too many to cover in this presentation. I just wanted to highlight one that is representative for this class of problems, which is a typical example of how some design decisions can favor fast development in scripts with pared down character sets like Latin and discourage rapid progress in complex scripts where an inordinate amount of shaping rules have to be developed. This is made even more difficult when the shaping and encoding models are fundamentally different. Thomas Milo's advanced composition engine, for example, not only employs different models, but it conceives of the relationship between a character and a glyph differently. It starts from typographic principles, modeling contrastive features of letter forms, and encodes the digital information accordingly, not the other way around. This ability to develop your own model is something that is currently not possible in the current infrastructure. This is why ACE was developed as a standalone piece of software rather than a font. Historically, the product lifecycle included a plugin, server, and others. The problem is compounded even further with alternative speculative models like probabilistic models, where glyph is conceived as a distribution in a latent space of possibilities, for example, or topological models. The list of similar examples is way too long to cover here, but the point I'm trying to make is that these alternative conceptual models have made significant knowledge contributions. Ideas such as style being contingent on fluid concepts, contrast being derived from transformation on a set of parameters, topology having the expressivity required to capture handwriting aspects, and so forth. But since they're not standard compliant, they are not made available to designers practically to use them, or do designers have easy ways of developing their own models. And the aim of this presentation was to start a discussion on the consequences of design decisions in digital type systems. In order to cultivate a healthy critical reflexive practice that can support sustainable, equitable global development, it's important to examine how these decisions can promote and enable particular modes of design production, obstruct others, and maybe ask questions on how to best balance plurality, diversity with universality and standardization. Thank you. I'm on time, yeah? Good, good, thank you.